Hi everyone, welcome to a new lab session and thank you for the response for the lab session one. Many of you appreciated. I'm so happy that you liked it. So before we begin the lab session, I just wanted to show you something cool because let's just look at some of the microcontrollers which I have here. So obviously this is a very famous one, the Raspberry Pi, and there is also an Arduino and Node MCU, but I don't have that because I don't work at that low level. So but this is a really interesting microcontroller, and many of you might be using it for your tinkering purpose. This is another one. Can you see that? STM32F407. So this is an ARM Cortex M4 processor inside this, which is really amazing. So ARM series is one which is currently industry standard. The architecture which we're studying is x86, 8086 architecture. Is little old, not little old, quite old. We don't use it now in our. Oops, I'm not able to take this out. Ah, I think it's stuck Oops, sorry. So here is that board. Now this is a really powerful microcontroller, and the power of the microcontroller actually depends a lot on the clocking, on the clock speed which it works, and the peripherals which it can support, the communication standards which it can support. So this is another board, STM32F407. This has a lot of sensors inside this, like the inertial sensor. Like if I just do the board like this, so there is a sensor, inertial sensor, which can measure all that. And here's the final one. I won't try even opening that because I might again fail, in taking out the board. Jokes apart, but this board is also really cool, and its name is STM32F303. This also has an ARM Cortex processor inside this. All right. So, but every what we'll see throughout the course is that we'll be writing assembly language programs. Now, these are the programs which can be directly converted to the byte code. But on top of that, there is something known as a high level high level programming language like the C code or the Python code. All right. And what these compilers, many of, like, for every board there comes a compiler attached with that converts the high level code into the assembly code which you can see, and that assembly code is translated to the byte code. All right, so there is a whole process in that, and hopefully we'll be seeing some example maybe in future lab session. So with that intro, uh, let's proceed with the x86 or 8086 architecture. So before we do that, a quick recap. So let's briefly go over through what was asked here. Move three addressing using three addressing modes. I think this might have been covered in the lecture by this point. So move the value 1133 into the register AX. So the answer for this is simple, that just move AX 1133. And the next part is swap the lower and the higher bytes in AX and move them into BX. So the trick is that it's already given actually that you can the AX can be broken up into AH and AL, same as BX can be broken into BL and BH, and then you just have to swap this. So instruction would be simple: move BH comma AL and move BL comma AH. And finally, move the value in BX to the memory location at an offset of 20 from BX. So the memory location, let me take out my pen. So the trick is simple, that just read what it is saying: memory location at an offset of 20. So if I write my move instruction like this, move, then the memory location at an offset of 20 can be written as bx plus 20. And what do I have to move inside that? The contents of register bx. So move the value in bx to the memory location at an offset of 20. So this is simple. And so similarly, the task 1, task 3 are also simple. If I don't want to write them down here because many of you might be giving a reattempt, so you might not think deeply, but the answers are simple. I'll just orally speak them that in the second task, move the first letter of your name to the location. So this is very straightforward. Just try to find out the ASCII character. Like if my name is A, then it corresponds to 61H, right? So move bx comma 61, and then in the ds, I at this location where they have told me to the location ds. So the location ds can be written as ds colon 120, and in that I have to move. So sorry. All right. So now let's proceed with today's lab session of follow along example. So like this is a very standard step of, you have to be really, what should I say? If someone wakes you up from the sleep and tells you that, okay, open the DOS box and open debug X. So this you should remember, mount D colon and D colon backslash massum 611 slash bin. So none of you should forget this. So firstly, let's open the DOS box and load massum folder as always. And for my coding, I prefer VS Code, and which is my preferred IDE. And I've installed the ASM extension onto this, so you can just do that on the uh, IPC PC as well. Now in that, what we'll do is open a folder workspace in VS Code. So let me do that right away and show you. In fact, I've already done that for me. So you can go to File and open workspace, open folder, and you can open the bin folder from this. There'll be a trusted settings on top. You can trust this, not an issue. Right. So now let's write an ALP for moving data in and out of the memory. But before doing that, it is important to have a discussion on what segments are. So you can imagine that your whole memory, whatever the size of the memory is, can be broken into four segments. And those segments are the logical segments. So those segments are all logical segments, because we're not dealing with physical addresses. From the microcontroller's perspective, we always deal with logical segments, which can be translated into actual physical segments. But these will consist of three components in our program, which will be a code segment, a data segment, and a stack segment. So mappings of logical. So let me actually make a memory map here and see. All right. So if this is our memory here, this can be of any size starting from the lowest location, pointing by this all zeros up to certain memory address, which is based on how many locations we have. So if we have, let's say, 64K, if we have 64K, then 64K, how many address lines do we have here in 64K? So I can break it down into 2 raised to the power 6 into 2 raised to the power 10, right? So K translates to 2 raised to the power 10, and 64 would be 2 raised to the power 6. So I have 16 address lines here. 16 address lines means how many bits I need? 16 bits to represent that, and 16 bits. So here I've written an extra zero, so it's just 000H up to FFFH. So these would comprise of 64K locations. If I have 128K, uh, then how many address lines do I need? Obviously just one more I would need, right? So that would give me 128K. So assuming that, let me just pointer options, erase all ink on the screen. So I say that let me draw a memory of size 128K. All right. And if I have defined all the segments in just so 64K would be approximately half of it, right? So let me start from this part, and obviously these are 64K. There is some latency in my pen and this screen, so therefore please bear with me. So the start of the segment, what we write as the data segment or the code segment or the extra segment in the tiny model which we'll be using. So there are many models to define that. As of now, all of them point to the same location, and you can see that in the DOS box itself. So let's just first open DOS box for now and try to see that. So as always, mount d \masm611/bin, changing to D drive, and opening debug X. So if I type in R command here, you can see that all of them are pointing to the same, all of the stack segments are pointing to the same memory location. So this is because of the tiny model that all this is happening. And in the tiny model, the maximum which a segment can have is 64K. Why is it so? Because let's say that right now it is containing 80 right? So I have to multiply this by 10h. So this is also h. I have to multiply this by 10h, and I have to add um, how, for the lowest memory location, what should I add here? 000h. And for getting the last memory location, what should I add here? FFFFH, right? So let me just quickly do that on the calculator itself. So if I have 0859, I can multiply it by 10. So 8590. So this is the physical address 8590 of this memory location which I'm making here. All right. And if I add FFFF inside it, then 1858F, this will be the memory location of the 1858F. 1858F. So this will be the last memory location. Together, if you just count how many memory locations we'll have in between, this would come out to be 64K. All right. So a little bit understanding of this is required for you to appreciate that why we are using the tiny model. All right. So having this understanding, let's proceed forward and try to see how it practically translates to code. So there are many models available in MASSIM assembler, ranging from tiny to small to huge. And to designate a model, we use the dot model statement followed by the memory model. For example, if you have to use the tiny model, we simply write dot model tiny. So the tiny model requires that all program and data fit into one 64K segment. And just as we discussed right now, that the calculation, the mathematics, how it shows is that the offset can only be of 16 bits, right? So the maximum offset can be FFFH, and the minimum offset can be 000H, right? So whatever your data segment is pointing to, the whatever is in between, the count will be maximum 64K count in between this. Okay, just an interesting exercise for you people, that try to find out what does 64K in hexa would mean. So that would be fairly simple. Just if you go to computation and 2 raised to the power, if you do 16, it would be this number 65536. Since we're counting from 0, so we'll have to subtract 1. So 65535. So if I go to base n and in decimal, if I type 65535, and guess what will it convert to in hex? FFFF. So that this is no magic actually. Um, everything basically adds up. Whatever your count is would be same. The count will remain the same. So continuing with our actually starting with our continuing with our follow along example, which we have just right now opened the workspace. Let's create this program in VS Code editor to store data into memory and do some move operations. So pause the video right now and take some time to create a new file and write your code there. I'll do it right now. Dot data, and so data one. So this part of the code which you see here, this part of the code is just like in your C program. How you begin your program is by initializing few variables, right, which will be used throughout your program, right? So this is exactly that part where we're just naming the variable. So data one actually is pointing to some memory location. So this conversion has to be clear to you. This conversion has to be clear to you. Uh, that data one is just the name of the variable, and the value which it is storing is 23, but it is pointing to some memory location. As a programmer, I don't need to know that, where in the memory my data has gone, but from microprocessors perspective it is important. So therefore, when we write our ALP, we are not much concerned with what is the where it has got stored in the memory. Wherever it has got stored, microprocessor will call it and will use it. You just have to write the algorithm right. But when we are debugging the program, it is sometimes important for us to realize that where my data segment is and how to display that. Because as an examiner, if I come, then you'll have to show me where that data has got stored, right? And that can be also part of your test. So you need to know how to figure that out. So let's write the complete code and then discuss this further. I've already written this code, so I'll just simply copy paste from there. There are a few additional things which I'll remove now. um, this 999, you can as well leave it to 9876, because this will give you even more clarity on uh, how this 769876, how in the little Indian format it is stored, right? So this is the move operation. So our focus right now would be on the data segment, that how this data segment is getting stored in the memory. All right. So let's compile and run the executable in debug X using the following commands. So, so I think this view would be better so that I can interact with you while I'm speaking. All right. So let's close this. The Q command is used to close this. Everything is clean right now. And the example one.asm, I have ensured that I've pressed Control S in order to save it. The first thing which I need to do is um, compile my ASM code and then run the executable in debug X. So for that, the command is ml, and I simply have to write the name of the file, ml ex1.asm. So now once if there are any errors, it will reflect here. If there are any compilation errors, syntax errors which you have made, and now you can run this executable, which you can see ex1.com. So the way to do that is debug x ex1.com. All right, so now we're in the debug X window. Nothing new, nothing great. It opens in the same way. But what is special here is that the instructions which I have written here, BX, CX, you can see are all coming here, right? So let's see the instructions using the U command. So here are the instructions. But hey, wait, I had written data 2, data 3, etc. But it is all replaced by some byte code, as you can see here that it's written for data 2 as 011D. For data 3, it is written as 011F. For data 1, it is written as 011C. So again, as I've already told you before, that this is for the microprocessor to understand. As a humans, we just have to write the variable names, right? And for this is for the microprocessor to understand that this is the specific memory location, and this is the job of the compiler to actually fit in all those variables with the memory locations which it has to be translated to. And these instructions are run as it is on the on the microprocessor. Okay, so now you know the answer that why this is replaced by bytecode. But then another interesting question comes up is that how to know which memory location my data has gone. So as you can directly see the trick here that in order to know that which all data has gone to which memory location, I can use the load effective address. So whatever is my data, so whatever my data is, data 1, the memory location, the memory location of that data 1, I can load into the SI by the instruction load effective address. And as you can see that the initial 4 instructions correspond to all the data. Now you have to understand this carefully, that all this um, all this load effective address is unnecessary when you're writing your comp paper or your midsem paper, because that time you're not concerned with the memory locations. That time you're just concerned with data 1, and throughout the algorithm you'll be using the word data 1. But for your ALP and for your lab sessions, it is important to know where that data has gone, because you'll be using debug X to debug the program, and you need to know that. Therefore, as a golden rule, like not as a golden rule, but as a sort of a recommendation, this is a good place to start your code, that you make a note of uh, all the memory addresses where your data has gone. And then what you can simply do is, so let's just proceed sequentially, that now the complete instructions which has been loaded into the memory are this. And we can directly since I've pasted all the screenshots, I think it will be quick to follow along this way only. So hey guys, hi back. The later half of the recording was not saved, so I'm recording it again today. I don't remember the exact things which I had spoken, but I taught in detail. Let's try to go through them once again. So as we discussed about the importance of seeing the memory locations, the data one getting pointed by 012C, 012D, 012F, 0131, pointing to data 1, data 2, data 3, and array respectively. Let's try to see what is the exact contents of those memory location, whether it even matches up with this 23 or not. All right. So let's go to the memory location of data 1. So as you could see that 012C pointed by the first memory location 012C here, as you can see here. So the first thing which is stored here is 17. But hold on, why is the 17 coming here? So the answer is actually right in front of you. I'll show this quickly to you. I'll open my calculator and do it for you. For those who are confused, downloads, Casio, right here it is. So from the mode setup, we go to the base n, and in decimal, we have 23. So obviously that would become 17 in hex. So this is storing in hex format, right? So the 17, and in the example we have 9999. So this lower significant bits are going initially going to the first memory location, and then this 99 is going there. So now let's experiment with db, dw, and other data to see how they are stored in memory. So I would highly recommend that you pause the video right now and try to make some of the adjustments here, like I've done it in the slides. Let me do that quickly. Let me pause the video for a second and load up the memory. So here I have my data with me, and as you can see, I've already made some changes. So let me try to add something here. Let's try to add a capital A, and 0. All right. And let's try to add the same things, but this time to the DW directive. So DP means that it's going to take up 8 bits. DW means that it is going to take 16 bits, right? And FE, I've kept it that. Let's keep it that way only. And let's save it. Oops. So ML example1 dot ASM, and now debug x ex1 dot com. So seeing the memory locations, that is pretty evident by now that why is it happening this way. By the way, I've not stored the LEA commands here. So 0120028, and the first memory location is for me 011C. All right. So I just keep that in mind. 011C. Although it's better to take a screenshot of this in the starting, but 011C is what we will remember. So at that memory location, I expect to find 17, and then the ASCII, whatever this ASCII of A, because I'm passing it within the quotes, so that is getting passed as an ASCII value. Okay, so let's go to that memory location CDS colon 011C, and here you can see that the value getting stored for instead of A is 61. For capital A it is 41, and for the number 0 it is 30. But all of them are taking just one byte each, right? Because what we have given here is dB. But when we are giving dw, the same A will now be represented as 0061. So therefore 61 will go first and then 00 followed by 41, then 00. All right, so that should make sense to you now. And if you play around with different characters, different lengths of strings, and let's say if I type my full name here, save it, and q debug x, you going back to the same memory location DEDS colon 011C. So here I can see my complete name coming here. All right. So many things will build up throughout the labs more on this, but take a pause, try to experiment with different things. Now let's try to get a data from a text file. So let's create a text file here, and I've already done it yesterday I did that. So again I'll do it today because unfortunately the recording got lost, got corrupted. But Apple star mup. All right. So I've written this in the data.txt file. You can create a new file using this button and can make that. Now how to bring that inside the memory. So for doing that, let me go to this. Oops. So we're in the debug X right now. Let me just quit from here and start the operation of just let me enter debug X. All right. So now there are no instructions. The memory is all clean. Everything is tidy. And let's try to bring in this piece of data. So for doing that, I'll use the N command and the L command. So the syntax for this is N, and just since we've loaded the bin folder only, so we're pointing to the current data. So therefore it will be just data.txt. And once I load it to any particular memory address, let's say I want to load it at the extra segment 0200. Then if I go to the extra segment 0200, then I'll see this Apple star mup written there. All right. So this is how I can load the data directly to my memory from a text file. And I can even write to a file that will come to later. Obviously, it's not required for this lab session. So the lab task is very simple. You can go through that and using the load command and the end command. And here for replacement, like if your name is 7 letters long, just go to the first memory location plus 7 and change this manually. Like there is no need to do a comparison operation, or don't overthink it. Just simply go to whatever the star memory location is, and then in order to replace that, all right, just read through it once, pause the video, read through it. So you have to replace that. So no need to overthink about this problem. Just simply go to this whatever memory location the star is pointing to, replace that with the ASCII character of the closing bracket, and replace and do a +3 to that star and replace this. Okay, +1 +2 +3 +4, the +4 would work, right? Whatever is this memory address, +4 of that would point to this memory address. And the ASCII characters. Now, many of you might be wondering, okay, if these ASCII characters, so this is nothing is magic here. Actually, nothing is magic. All this you can get, and the program to do that is very simple. In fact, the more expert you become, not in just this assembly language programming, but even for your normal C coding, you need to be in a mood of experimenting things, tweaking things. There is no such thing as spoon feeding. So if you're not able to understand something, just you can simply, if you want to find out the ASCII value, it's so simple. You just type and you find the ASCII of the closing brackets, and you find out the of the asterisk symbol. Okay, let's save it and mlex1 and debugx ex1.com. So going to the memory address C11C, 011C DDS 011C. Here you'll find the hex code is 5B, 5D, and 2A. 5B, 5D, and 2A. So, as I was telling, nothing is magic here. All right. Oops. I think because of my some things were not being you were not able to see this half of the screen, this small portion. But anyways, the concepts are clear, I believe. So that's what the next slide is about, how to figure this out. And that is pretty much it. So just few final piece of advice before you leave is that know how to use your calculator properly in hex mode, decimal mode, binary mode. These operations will be very prove to be very useful. And the data like getting to know, you need to understand the difference between ALP, what ALP as a human we are writing, and what ALP is being understood by the machine. Machine is just understanding byte code, so the compiler fills up all this data what you see here right now, 012C, 012F, sorry, the data 1, data 2, by this byte code of the memory locations. So that job is done by the compiler, and now the microprocessor just has to go to that memory location in order to figure out things. All right. So that is it from this video, and thank you so much. Bye.